So today we'll discuss some direct applications of Sylow's theorems. So the first theorem, the first application that we are going to discuss today is this. Every group of prime power order is solvable. So there are two things we need to remember: prime power order and solvable. Prime power order, another word is actually a P group. So every P group is solvable. Prime power order means so let G be a group with the prime power order, and that means order of G is equal to P to the power of n for some n integer n. And another word in this result is solvable. So a group is solvable if it has a composition series where all factor groups are abelian. That is the definition of solvability. Now, composition series means a subseries, a subnormal series where every factor group is simple. So, and the simple means a group is simple if it does not have any non-trivial proper normal subgroups. So those are the things to remember when you try to prove this result. So from the first Sylow's theorem, see, the order of G is P to the power of n. Then, for the first Sylow's theorem, for every I 1 less than or equal to I less than or equal to n, there exist subgroups of order Pi, and for every subgroup of order Pi, there exists a subgroup of order p to the power of I plus 1 such that pi is normal in pi plus 1, where 1 less than or equal to I less than n. So this is the first Sylow theorem. So that means there exists a subnormal series 0, this is actually equal to h1 less than h2, sorry, this is h0, h1, hn is equal to g, where hi is equal to the subgroup of order pi, where 1 less than or equal to I less than or equal to n. Using the first Sylow theorem. And this implies, so in this subnormal series, each factor group of this subnormal series is of order p, implies factor groups are simple. That implies subnormal series is a composition series. And since the factor groups, the order of the factor groups are p, each of the factor group is of order p, implies factor groups are cyclic and hence they are abelian. And that means G is solid. So the next part of the result, it's a definition called class equation of a finite group. This does not use any of the Sylow theorem, but this is actually a classification of or equivalent classes of or disjoint classes of a group. We have seen that if X is a G set, then we can decompose X into orbits, disjoint orbits. But similarly, we can decompose a group also. And we have a nice relationship between the order of group and the classes which is derived from that equivalence classes. So that equation is called class equation. Class equation of a finite group. Finite group. We know that if X is a finite G set where G is a finite group, then the order of X is equal to the order of the number of one element orbits plus if there are S number of one element orbits, then this will be S plus 1 to R GXI, where GXI is the orbit containing Xi, and I varies from S plus 1 to R, and R is the total number of orbits. We already seen this. So this is for any action. So we are going to define a particular action and a particular X. So let X is equal to G and define the action. Action is from G X to X, right? So this is actually our G again, and this is also G again. So take an element from here and take an element from here, and that goes to GX G inverse, the conjugate of X under that element. So this is the action. So verify that this is a group action. Definitely this belongs to G, and that is equal to X. So the only part which needs to verify is if you take two elements, then G1 G2 of X is equal to G1 of G2 of X. So we apply this one here. So what does this mean? This means that order of G is equal to order of GG plus S plus 1, or this I am going to take it as S plus 1 now, but we'll have another value here of GXI. And we have another, we'll come to that later. Let us find out first what is GG. GG is equal to X belongs to G such that the action of X on G for every element in G is equal to G. That means GX G inverse equal to X for all G in G. And that means that is equal to X belongs to G such that Gx equal to Xg for all G in G. And this is nothing but the center of G. Okay, and is a subgroup of G. Okay, now this GXI, each of GXI, this is the elements in orbits containing Xi, divides the order of G. So this can be written as So the equation 1 can be written as the order of G is equal to elements in center of G, we'll call it as C, plus sigma n I C plus 1 to R, where each ni divides the order of G. So this is actually going to be C, in other words, C plus n, C plus 1 plus dash 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 and R. This is called the class equation of the group G. Actually, what is happening here is the group G is divided into disjoint classes by conjugation. Conjugation is the action we defined here. So this is just to define the class equation. There is no Sylow's theorem used here. Okay. The next result is the center of every P group is non-trivial. Okay, P group means its order is of P to the power of n for some n. So let G be a P group. Implies G of the order of G is equal to P to the power of n for some integer n. So using the class equation, order of G is equal to the order of C of G plus sigma C plus 1 to R Ni. And this implies and each Ni divides order of G. Okay, so that means each Ni divides P to the power of n, and that implies each Ni are P to the power of I of P to the power of Ni for some integer Ni. And that implies, see, each and every element of this is a multiple of P. And this is a multiple of P. So this cannot be 1. This has to be greater than 1. So that means this implies the center of G, the order of center of G is greater than 1. And actually P divides center of G. And that implies center of G is not trivial. Now we are going to discuss a very easy sub-result, which is not going to be using the Sylow theorem, but we are going to use this lemma or sub-result for some other Sylow theorem related applications. So the lemma or result is this: if H and K are normal subgroups of G and H intersection K is equal to E and H join K is equal to G, then G is isomorphic to HK. There is a good example when G is a abelian group. And a graphical example is like this. So G is equal to R square. So H is this, and this is our K, and the only intersection is E, that is 0, 0, and H join K is equal to G here. I'm going to explain what this join is. You already defined earlier, but I'll go through that one more time. Then if you take any point here, that is actually HK, and that is belongs to, this is a point in G and this is a point in HK. So that is what we are going to prove, but we are not sure about what kind of group is G. Okay, so this is in terms of R square. When G is R square, this is what it is. And H join K is the smallest subgroup containing HK. And what is HK? HK is equal to elements of the form HK such that H belongs to H and K belongs to K. This does not need to be a group. So the smallest subgroup containing HK is called the join of H and K. And when K is normal, when K is normal, H join K is equal to HK. We are going to use this result here. So let us define HK here. HK is equal to HK such that H belongs to H, K belongs to K. Okay. Now we will take an element, a commutator element, HK, H inverse, K inverse. This actually belongs to H. because H inverse K inverse can be written as H times K H inverse K inverse. And because H is normal, this is in H. This is another element in H. So two elements in a group, so this belongs to H. Similarly, HK, H inverse, K inverse belongs to K because HK, H inverse, K inverse equal to HK, H inverse, K inverse. So this belongs to HK, H inverse, K inverse belongs to H intersection K. And that means HK, H inverse, K inverse is equal to E. And that implies HK is equal to KH. And since H and K are normal in G, H join K is equal to HK, and that is equal to G. Now we'll define, see, we need to prove that G is isomorphic to H times K. So that means we need to define a isomorphism. So define a map phi from H times K to G by phi of HK is equal to HK. We well defined. Okay. Now phi is a homomorphism because phi of H1 K1 H2 K2 is equal to phi of H1 H2 K1 K2, and that is equal to H1 H2 K1 K2. And that is equal to, see, H2 K1 is actually K1 H2 because of this. See, if you take an element from H and element from K, it commutes. So this is equal to H1 K1 times H2 K2. And that implies that's equal to phi of H1 K1 times phi of H2 K2. So this is a homomorphism. Now phi is 1, 1 because the kernel of phi is equal to HK such that phi of HK is equal to E. And that implies HK such that HK is equal to E. And that implies HK, H is equal to K inverse. And that implies it is just E. Because, because H is equal to K inverse, that means K inverse belongs to H because H is a subgroup. Similarly, H belongs to K. So H and K belongs to H intersection K. And that means it's only E. So this could be only E. So the kernel of this is E. So that means phi is 1, 1. Phi is on to because of this. G is equal to HK. For every element in G, we can express that in H comma K. That means for every element of G, we have a pair HK in H cross K such that phi can be mapped. And that implies phi is a isomorphism. And that implies G is isomorphic to H. Now we are going to use this lemma for an interesting result. Theorem. Every group of order p square is abelian, where p is a prime. Very interesting result. The way we are going to show it's an abelian is to show that if G is the group of order p square, G is isomorphic to H cross K, where H and K are subgroups of G. If we can prove this one, then G is abelian. Because if this is isomorphic to H cross K, it's also isomorphic to K cross H. That every element of G, the same element can be expressed in H comma K and K comma H. And that means that element is equal, so that means HK is equal to KH, and hence they are abelian. And that is the way we are going to show. Normally we don't show like this. If you want to show a group is abelian, you take two elements from here and see that it commutes. But that is not the way we are going to show here. Now there are two situations here. Case 1. Let G be a cyclic group. If it is a cyclic group, that means G is abelian. There is nothing to prove. All cyclic groups are abelian groups. Now case 2. Let G be a non-abelian group. Sorry, non-cyclic group. So, using the first theorem, first Sylow theorem, there exists a subgroup of order P. For P. So, since P is prime, this subgroup has to be cyclic. Has to be cyclic. There's no other way. So let A be a cyclic subgroup of G of order So that implies G is not equal to E. So what you will do is let B belongs to G minus a complement of A. Okay? So then B is a cyclic group, cyclic subgroup of G and must be of order P and is of order P because there is no other divisor, and this cyclic group intersection, this cyclic group is just the unit element, because if there is any other element other than E, that would generate both A and B, which is not which is a contradiction to our assumption. Because if C belongs to, C is not equal to E and C belongs to A and B, then C generates A and B, which is a contradiction. Okay, so A join B is equal to G because the order of A is equal to P and order of B is equal to P and order of G is equal to P square. Now we will use the previous lemma. This implies from the previous result G is isomorphic to these two subgroups, and that implies G is. So one more interesting result using that lemma which we established earlier. Let G be a group of order PQ where P and Q are primes such that P is less than Q, then G is not simple and if Q is not congruent to 1 mod P, then G is cyclic. And of course, if it is cyclic, it is abelian. Very interesting result. Proof is not very complicated. Since order of G is equal to PQ, there exist Q, there exist Sylow's Q subgroup of order Q, because it is the maximum power of Q is 1. So the Sylow's Q subgroup should be of order Q, and the number of Sylow's Q subgroup is 1 or is 1 mod P, 1 mod Q, 1 mod Q. Since P is less than Q, the number of Sylow's Q subgroup has to be 1. Because P is less than Q, and the next number will be Q plus 1, which is not possible. So it has to be 1. And that implies G has only one Sylow P subgroup. Sorry, Sylow Q subgroup. And that implies Sylow Q subgroup, let us call it as Q, is normal in G. We have already shown this one earlier. If there is only one Q subgroup, Sylow P subgroup, then it is normal because all its conjugates are Q itself, and those conjugates are the Sylow Q subgroups. So that means Q is normal. Now, using the similar argument, and it is given that Q is not congruent to 1 mod P, the number of P Sylow's P subgroups is also 1. Implies the Sylow P subgroup, let's say P, is normal in G. So this implies order of Q has to be P, and order of Q has to be Q, and order of P has to be P. Implies Q and P are cyclic. And Q intersection P is equal to E because every element of Q is Q and P is P. So there is no other element common to both Q and P. This implies Q join P is equal to G. This has got PQ elements and both of them are subgroups of G, and that implies Q join P is equal to G. So this satisfies all the conditions in the lemma. And this implies that G is isomorphic to Q. Since Q and P are cyclic, Q is isomorphic to ZQ and P is isomorphic to ZP. And that implies G is isomorphic to ZQ times ZP, and that is cyclic because P and Q are distinct primes, and that implies G is also abelian. Very interesting result using the Sylow theorems.